So we were talking about chemical formulas and that there are different kinds of chemical formulas. And we're going to learn how we can calculate an empirical formula for a compound. And in lab today, we're actually going to do an experiment where we get data that allows us to calculate an empirical formula. So empirical means derived from or guided by experience or experiment. So this is not really a theoretical thing. This is okay, we weighed this and we weighed this and we're going to figure out what the formula is. The empirical formula gives the smallest whole number ratio. It does not tell us the actual number of each type of atom in a molecule. So we should probably have an example or two here. There's, you've probably all heard of the compound hydrogen peroxide. The formula for hydrogen peroxide is H2O2. If we determined that formula experimentally, if we determined the empirical formula, we would come up with a ratio of 1 to 1. Because that's what the masses of the elements would tell us, that there was one hydrogen for every one oxygen, and that is true. And yet, in a molecule of hydrogen peroxide, there are 2 atoms of hydrogen and 2 atoms of oxygen. And so the molecular formula is the true formula of a molecule. The molecular formula is always going to be a whole number multiple of the empirical formula. The empirical formula is like the reduced fraction. It's the lowest ratio. And sometimes it is the same as the molecular formula. In that case, the whole number that you would multiply it by is just 1. But sometimes, like in this example, the molecular formula is the empirical formula multiplied by 2. So we're going to learn how to calculate the empirical formula. So here's one sort of an experiment that you could do to find the empirical formula of water. You can decompose water by passing electric current through it. And you can actually do that with a 9-volt battery. And in this setup, they're collecting the gas that's given off. When you pass electric current through water, you break it down into oxygen and hydrogen gas. The gas can be collected and you can determine the mass of it. So here they found that decomposing some water gave 3 grams of hydrogen and 24 grams of oxygen. From that information, you can determine an empirical formula. So here are the steps. And I'll go through these, and they may not make much sense until we do an example, but this is a good slide to refer to. We have to start with the masses of each element. So if you're doing an experiment like the water one or what we're going to do in lab today, you're going to have a mass of each element. The empirical formula, though, can also be calculated from a percent composition. So if you're given a percent, you can easily convert that into a mass by just saying, well, what if we had a 100-gram sample? If something was 25% oxygen and you had a 100-gram sample, how many grams of oxygen would you have? Well, 25% of 100 is just 25. So if you're given percentages, all you have to do is take off the percent sign and put gram. Easy. Okay, so you start with masses. The second step is to convert each mass to moles using the appropriate molar mass. We get that off the periodic table because the ratio that we're looking for is atoms to atoms. And so we have to go from a mass to something that deals with particles. And moles deals with particles. So we convert masses to moles. And here's where your book does it a little differently than I would do it. They say write down a pseudo formula using the moles of each element as subscripts. And you're welcome to do it that way if you'd like. And then take those subscripts and divide by the smallest one. Those subscripts are not going to be nice whole numbers. They're going to be messy decimal numbers. The way we turn them into whole numbers is by doing ratios. So if we divide them all by the smallest divided by itself is 1, and all the other ones will be greater than 1. Sometimes when you do that, all the subscripts end up being whole numbers, and other times they don't, and we'll see an example where they don't. Well, what if they're not whole numbers? Well, then you have to multiply them until you get whole numbers. So we'll go over that. So here's an example. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of 83.65% carbon by mass. Determine the empirical formula of the compound. So, empirical formula, we need the mass of each element. That must be somebody's car alarm. We need the mass of each element. Well, what two elements are present in this compound? Carbon and hydrogen. So we've got carbon and hydrogen. Well, they tell us it's 83.65% carbon. So there's an example where we're given a percentage, but we need a mass. So we just say, well, just say we have 100 grams, and then that's going to be 83.65 grams of carbon. How can we figure out the mass of the hydrogen? Subtract it from 100. Okay, if 83% is carbon, the rest of the 100% must be hydrogen. Love this calculator, but you can't get it out with one hand very easily. So 100 minus 83.65. That tells us that the mass of hydrogen, bless you, is 16.35 grams. So that's the first thing we have to do, is get the masses of all the elements. Now we're going to convert those masses into moles. So we use the molar mass, and we learned how to do this on Tuesday. So we're going to divide by grams and multiply by moles. We look this up on the periodic table. 1 mole of carbon weighs 12.01 grams. So we take our 83.65, we divide by 12.01. .965 moles of carbon. And for hydrogen, we do the same thing, moles of hydrogen, and the molar mass of hydrogen is 1.008 grams. And this comes out to be 16.22. Now, I did round those numbers to 4 significant figures. That's what the rules of sig figs say is appropriate there. And I don't have a lot of space here on the slide for scribbling. It's better to keep more digits. Okay? You definitely do not want to over-round when you're doing a calculation like this. And sometimes, I don't know what gets into students' heads, but they'll round 6.965 off to 7, and they'll round 16.22 to 16. Don't do that here. Okay? Keep at least the required number of significant figures. It's better to keep more. More will not hurt anything. So 4 is good. I definitely wouldn't go below 4, even if your initial numbers only had 2. I would just keep the 4. So then your book tells you to use these numbers to make a pseudo formula. I just kind of skip that step. I'm looking at these two numbers, and I need the ratio. So I'm going to pick the smallest, which is 6.965, and I'm going to divide both of them by 6.965. Whatever we do to one of these numbers, we have to do to the other because we can't change this ratio. So the first one ends up being 1. You'll always get 1 that's exactly 1. And then 16.22 divided by 6.965 gives us, let's see if I can fit it in here, need some space here. 2.329. So the ratio of carbons to hydrogen is 1 to 2.329. That's not a whole number. And that's not close enough to round off. You can't just round it to 2. So then what do we do? Well, we need to multiply both of these numbers by something. So if you're familiar with decimal equivalents for fractions, you know that 1/3 is 0.33 repeating. And this 0.329 suggests to me that this number is 2 1/3. And if I multiply it by 3, I'm going to get a whole number. So if I take that number and times 3, I get 6.986. Yes?
So we're just supposed to kind of know this?
Well, I'm going to tell you. I'm going to tell you the other way. So that's if you're familiar with decimal equivalents for fractions. No, I don't expect you to know that. Most students don't. So what if you're not? Then you do the trial and error method. You see 2.329, you say, okay, well, that's not a whole number. So then first I'm going to start by multiplying by 2 and seeing if that makes it a whole number. So 2.329 times 2 gives me 4.658. Still not a whole number. Well, then I'll go to 3. 2.329 times 3, 6.897. That is really close to 7. These are experimental calculations from data. And so it's not going to come out perfect. It's going to be off just a little bit because there's error in measurements. And so how do you know what's close enough to round? Well, my rule of thumb, just a kind of a guideline, is if it's less than 0.2 away from a whole number, then it's okay to round. So we look at this number, 2.329. The closest whole number is 2. But the difference between this number and 2 is 0.3. That means we can't round that one. Let me erase this. So I'm going to multiply this one by 3, which will give me 3. And I'm going to multiply this one by 3, which gave me 6.987. 6.987 is less than 0.1 away from 7. Do you see that? If I subtract that from 7, the difference is 0.013. That's close enough to round. So I can round this to 7. So what I've got here is a ratio of 3 to 7. Those become the subs... what did I do? Those become the subscripts. So C has a subscript of 3, H has a subscript of 7.
So we have to have a whole number each time?
You have to get whole numbers because all of our chemical formulas are whole numbers. Because in a molecule, you have to have a whole number of atoms. You can't have 1.5 atoms in a molecule.
On page 185 in our book, we're given a chart of the multipliers to use to come up with a decimal.
Yep, that works, the chart in the book.
That doesn't fall into that.
It didn't fall into that?
No, it doesn't say 0.32.
So the original ratio was 6.965 to 16.22. But those are messy, non-whole numbers. And so this dividing and multiplying business is just to find the whole number equivalent of that ratio. So let's do this. If we take, well, we already did it, but if we take a ratio of 16.22, which is the moles of hydrogen, and divide that by the moles of carbon, 6.965, we came up with 2.329, right? And here, after doing all this manipulation, we've got a ratio of 3 to 7. Well, what happens if you divide 7 by 3? You get 2.333, which is very, very close to 2.329. Okay, that's within experimental error. It's not going to come out perfect because it's real. Nothing real is perfect. This is just a math technique to find the whole number ratio. And we'll do some more examples. We're going to actually do this in class today, and so you'll have lots and lots of questions. Any other questions right now?